All right, so today's lesson is going to be on complex numbers and them being in polar form. But before we get started on that lesson, I thought it'd probably be a good idea to remind ourselves what complex numbers are. So I've got these expressions here. It shouldn't be too bad, but what is a complex number? So remember, a complex number is when you have something like a plus bi, and a is the real number. Whoa, a is the real number part, and b is the imaginary part. So a is a real number of sorts, could be positive or negative, and then b is the imaginary part, bi, right? Because it's got the imaginary number I with it, right? So we can do all kinds of stuff with it. We can add, subtract, multiply, divide. We can do some pretty wild things. We can square root, do a bunch of crazy things. So we're going to kind of wrap up this unit messing around with how does complex numbers relate to polar and what are the benefits. So should be pretty good. So let's just go through this. I squared. Do you remember what I squared is? I hope so. I squared is -1, then minus 4i, and then -6i plus 12i squared, right? I'm just distributing those. So I squared again is -1, so that makes -12. And then what would we get? Let's see, we get -13 minus 10i, okay? So that would be a complex number, right? You see your real part and you see your imaginary part. And you can't combine them because you can't combine real numbers and imaginary numbers. But it's okay with them working together. So I'm going to multiply this out. That'd be 16 plus 8i plus I squared. I squared is -1, so that would be 15 plus 8i. Okay. If somebody says, what's the sum of problems 1 and 2, then I'm just going to combine like terms. So -13 plus 15 is going to be 2, and -10 plus 8i would be -2i, so -2i. Okay. So today, just to kind of give you a heads up, what are we going to do with this? We're going to graph it. What? Right? And then we're going to put it in polar form. Okay. And what else are we going to do? We're going to maybe find like the absolute value. But I might have gone out of order there. So we're going to do 3 things. Shouldn't be too crazy, but should be a little bit of fun with that. Last question. Do you know what I cubed is? Do you remember if you keep like raising I to a power, what you end up with? It's just for fun. Remember, there's only 4 things that you can get for I. So I to the first power is just I squared, which we use all the time, is -1. I cubed is -I, and I to the 4th is 1. Okay, and then it just cycles back through those again. I don't ask that for too many reasons. I just ask it because I like to. All right, so anyway, the idea is complex numbers. Hopefully that makes sense and should not be too crazy for us to do. Okay, all right, so here we go. Polar form of complex numbers. So we should feel comfortable taking a point, xy, and moving it into a point, r comma theta. Okay, we should feel comfortable taking an equation that's in rectangular and moving it into an equation, right, that's in polar. What else should we also feel? I mean, and for these cases, you should be able to go back and forth. We should be able to graph an equation that's in polar. And now we're going to take a complex number, right, that is a plus bi, and we're going to move it into its polar form, which is r equals, just kidding, z equals, no. Oh man, can't find my button on my stylus to erase. It's like been the bane of my existence since I found that I'm doing most videos in the dark since people are asleep. So z equals r times cosine of theta plus I r sine of theta. And we'll talk about another way you could write that. So we're going to go in from, this is kind of like rectangular form, but we'll just call it complex number form. And then it goes into polar. This is the polar form of a complex number. All right, and we're going to talk about how we do that today. So we got to start by first graphing complex numbers, and then we'll move them into polar form. So we can say that a complex number is z, so that's a plus bi, and it can be graphed in the complex plane by plotting a and b. Okay, so complex plane. So now we have our third plane that we can work through. All right, so this one's actually super easy. It's just like a rectangular plane. The x-axis is considered the real axis, and the imaginary axis is the y-axis. So nothing crazy. Sorry, I'm drinking some coffee. This is happening. So if you hear a little bit of coffee drinking, just know that the fuel must get in the body. All right, so let's just make up one. Let's say 3 minus 4i, right? So I'm going to say that if that's what I'm graphing, let's say this is z. Okay, I'm going to plot z. 3 is the real number, so 1, 2, 3, and then -4 is the imaginary part. So 1, 2, 3, 4. Boom, plotted a point. We're amazing. That's z. It's literally that easy. So 3 minus 4i will be in quadrant 4. You know, like if we did z equals, I don't know, 10 plus 5i. Right now we're just saying, oh, 10, that's over here, and 5, that's over here. And so then we'll call it z2. Excuse me. Right, so 10 plus 5i. You'd have z2 in the first quadrant. So it's just literally just plot the point as if it were x comma y, and you'll be fine. Okay, so a little bit of practice. If you want to do this without me and hit pause, you can, and then we'll come back to the other. So, you know, if you hit pause, great. If not, here we go. So z1 is going to be in quadrant 1 over 2 of 3. There you go, z1. Z2 is going to be in quadrant 3, 1, 2, 3, 4, 5, and then down 6. 1, 2, 3, 4, 5, 6. Okay, that's Z2. And then we're going to add these suckers. Okay. -3. Do you agree? -3. I hope so. -3 and -3i. Okay, so where's that? That's here. 1, 2, 3. 1, 2, 3. There's z1 plus z2. Oh, multiply. Look at us getting wild. So 2 plus 3i times -5 minus 6i. Let's go. -10, -12i, -15i, -18i squared. Booyah. All right. I squared is going to be -1. So -1 times -18 is 18. So it's going to be 8. And then minus 27i. Does this seem right? That seems right. Maybe it seems right. All right, so I'm just going to kind of go off the map here. 1, 2, 3, 4, 5, 6, 7. And I am not counting 27. Let's just say that it's somewhere down there. So this is z1, z2. I hope I did that right. Okay. So anyway, that's how you plot a complex number. It's not too crazy, right? So let's try to tie this into what we're doing here today. So let's go to this one. We're going to plot it, and then we're going to see if we can figure out the distance from the origin. All right, so here we go. I'll give you a second to plot it on your own if you want. If you don't want any hints, you know, that should be good. Okay. All right, -6, 1, 2, 3, 4, 5, 6, and then up 8, 1, 2, 3, 4, 5, 6, 7, 8. So I got quadrant 2. This is Z, and we would like to figure out the distance from the origin. Boom. I feel like we've been doing this forever. Like this is like something we've been doing since last semester. So on the count of 3, you and I are going to say how we would find the distance from 0, 0 to Z. On the count of 3, we're going to say, here we go. Ready? On the count of 3. 1, 2, 3. Pythagorean theorem. Whoa, way to go, team. Oh, we're amazing. Somebody saying, how would, I didn't say that. Okay, well, if you just, any point can make a triangle, you know what I mean? We can't really count diagonally. So any point can make a triangle. We went 6 this way, we went 8 that way. And so you have a right triangle. You can always find what, I mean, if you start to think about it, this is really like when we were doing trig stuff, this is the radius, okay? Or even just polar stuff from this unit when we were plotting x, y, and then finding the radius. There it is, right? So this is the same thing. So if somebody says the distance from the origin, it's just the radius. And hopefully you know your Pythagorean triples. On the count of 3, we'll say our answer. What's the radius? 1, 2, 3, 10. Way to go, team. You guys are the best. All right. Now let's just say if you didn't know that it was 10, you'd go 6 squared plus 8 squared equals r squared. You need square root. And so r equals the square root of 36 plus 64, which is 100. And the square root of 100 is 10. All right. So anyway, that's the distance from the origin. Now, why am I pointing out this idea of the radius? Well, because when you're dealing with complex numbers, it calls it another name. This is the most annoying thing about mathematics. I'm just going to be 100% honest, okay? The most annoying thing about mathematics is based off the different area of math you are in, they use different words, and we've all kind of seen this happen in our math lives before. So this really fun word to say though, modulus, okay? The modulus or absolute value of a complex number, okay? And really all you need to do is think, all you're finding is the radius, right? So think radius, okay? So radius being, right, the point, the origin to the point, right, the distance of the origin to the point, or complex number. The modulus, okay, is considered the absolute value of the complex number. So check this out, right? So you have z, it looks weird, but it's really not bad. Take a look, right? You have z, which is the complex number a plus bi, which doesn't scare us. And they're saying that the modulus is the absolute value. So there's our absolute value bars around z. And it says the way that you find it is you literally just do the Pythagorean theorem, right? So you're finding the radius. So it's the square root of a squared plus b squared. Simple enough, okay? So don't let it freak you out too much. So here's the thing, if you need a visual for this, I'm going to plot the point really quickly. So -8 and 5, so in the complex plane, right? This is the complex plane. So where the x-axis is the real part, and don't need that much. The x-axis is the real part, and the y-axis is the imaginary part. This would be -8 plus 5i. So if you're needing the visual, what we're saying is the modulus is the distance from 0, 0, right, to the point. And if you think about absolute value, when you first learned absolute value, hopefully your teacher told you that it's not like, I'll just make it positive. The absolute value is a distance, right? It is the distance of that number from 0. So like how far away is it from 0, which is why it's always positive, because distances are always positive. So the modulus is the distance, okay, from the origin to the point of the complex number. And so that's why you end up with this. You can always end up creating a right triangle, and the real part will always be this side of the triangle, and the imaginary part will always be the vertical side. And then you can just do the Pythagorean theorem. So it's always going to work out to the square root of, some of us are doing, like, if you were doing the Pythagorean theorem here, you would write this, -8 squared like that. Just so that we're clear, that would be -64. And that would be bad because when you get -64 plus 25, that would be a negative number, which then would be an imaginary number for the absolute value. And I'm just going to say this, while we are working with imaginary numbers, you won't ever get a modulus that is imaginary. So don't do that. What I would have recommended is put parentheses around the -8. That way you'll get 64, especially if you're using a calculator, right? This is 64 plus 25, which is 89. And I don't think that simplifies, right? I think that's good. So the modulus of this guy is the square root of 89, or think radius, okay? So this is the square root of 89, if I want to add it into my picture, okay? So pretty straightforward. Hopefully that doesn't bother you. We're just going to move right into it. I don't think we need to spend a ton of time practicing the Pythagorean theorem. So we're just going to move into kind of the final part of the day, right? So the final part of the day is this, right? Polar form of complex numbers. So we already know the complex number is z equals a plus bi. Not a problem, okay? But then there's this polar form or trig form, depending on who you're talking to, right? I told you it's the annoying part of math is they all have these tons of different names. But the polar form or trig form can be found like this: z equals r cosine of theta plus I sine of theta. Or if you want to distribute the r, you could say z equals r cosine of theta plus I r sine of theta. Now let's, or r I sine of theta is probably the way I would write it. Now let's talk real quickly about, man, this seems weird, but maybe it's not as weird as we think. Okay, so let's just take a quick 2-second break. If I were to tell you to convert, and we're nearing the test is in a week, okay, week from today. If I were to tell you to convert xy into r theta, right? Say, okay, there's a point. You should know how to do this now. So step 1 would be what? Step 1, you would say find the radius. Yes. Step 1, you would say find the radius. Okay. And then step 2, right, you would say find the angle. And how do you find the angle? You would say, the angle is done by doing the tangent of theta equals y over x. Okay. So that's the first one. If I were to ask you, then walk me through, how do I convert r comma theta to xy? You should also know how to do this one, right? So if I were to ask you to go back, what would you say? You would say that, oh, these ones are actually easier. You do x, and that's r cosine of theta, right? And you do y, which is r sine of theta, okay? So we're going to use all of this, but let's just talk about that second one right there that we just said. R cosine of theta pops up. Well, where does it pop up? It pops up as the real part, the a, okay? And what was that in the complex plane? The a part was the x-axis, right? So it makes sense that the polar form of a complex number is the first part is r cosine of theta. Then if you look at this, right, we have r sine of theta, essentially the I, we don't normally put it at the very back. But the r sine of theta right there, we can. But that is acting as the b, and the b was the vertical part, right, on the complex plane. And what is r sine of theta? R sine of theta is the y, which is the vertical part. So it makes sense that for a complex number, the polar form just correlates to what we already were using. the horizontal part is r cosine of theta, and the vertical part is r sine of theta. And we just have the I in there. So we're not like really branching out too far. And then the last thing is, take a look, right? Where r, okay, is the modulus. So it's like you could have just called it the radius, but whatever. So r is the modulus, which we just talked about, and you do the Pythagorean theorem. Just like with polar, right, to find r, find the radius, you did x squared plus y squared equals r squared. So it's the same thing. And then the argument is theta. So tangent of theta equals b over a, or tangent of theta equals y over x, like we did. Okay. So we're really actually going to do basically just this step. These are the steps to convert. So hopefully it's nothing too crazy. But we might actually have to do a little extra thinking since we have to make sure that the angle is in the same spot. So before we get started, let's ask, which quadrant is this complex number in? On the count of 3, 1, 2, 3, and everybody says 4. Yay. So this is in quadrant 4. Right? You move to the right and then you go down. So all I'm saying is that your polar form should be in the same quadrant as your, what's it called, complex form. Okay, so first thing we're going to do is we're going to find the modulus, so the radius. And to find the radius, you're just going to do the absolute value of z. Okay, if you want to think of it that way, or if you just want to think of it as r and not try to add any more to the brain space, then okay. But it's the square root of a squared plus b squared. And so a is 4. So we have 4 squared plus negative 4 squared. So 16 plus 16 is 32. And we will simplify that. So what's that? 4 rad 2. So the radius is, or the absolute value of z is 4 rad 2. Okay, so there we have it. Next one, we need the angle. So we're going to find the angle. Okay, so tangent of theta equals 4, oh, just kidding, negative 4 over 4 y over x. Thank you. And so that's negative 1. So tangent of theta equals negative 1. So I'm not going to use the inverse at the moment for this, just because tangent being 1 is a good thing. I'm just going to think of what angle would be in the 4th quadrant that would make that true. Do you know what I mean? Like kind of solve it like an equation, because I know I needed to have it in the 4th quadrant. And at the moment, there's no restrictions on me. You just need to read the instructions. So like if the instructions say, you know, your angle has to be from 0 to 2 pi, then make sure you just pick an angle that's from 0 to 2 pi. If your instructions say that it's like in the homework the other day, it was like negative pi to pi, then, you know, make sure you're following that. But since they don't give us anything, where's tangent negative 1 in the 4th quadrant? I think that would be, I'm just going to hit up 7 pi over 4. Okay, that would make it true. Okay, the last step though is you actually have to write the number. So what do I mean? I mean like 4 minus 4i becomes z equals, the radius is 4 rad 2, okay? And then you get cosine of 7 pi over 4 plus I sine of 7 pi over 4, okay? I am not going to multiply that out. And here's what I'm going to ask you. Well, riddle me this, friends, okay? If I were to multiply this out, like figure out what cosine of 7 pi over 4 is, which is rad 2 over 2, and sine of 7 pi over 4, which is negative rad 2 over 2. If I figure out what those are, and then I multiply them, I really want you to think about this. If I figure out what those are, and then I distribute the 4 rad 2 into this, what do you think I'm going to get? Like, this is super important as to why I'm not going to multiply this out. What do you think I'm going to get if I were to multiply all that out? Figure it out, multiply it. I would get, dun, 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 dun. I would just get back to you. And so it does you no good. You just undid everything that you worked hard for. So we're just going to leave it as this polar form, and we're going to call it good. So this is my answer, and booyah. All right. We are feeling good. So really, there's not a lot of new stuff happening here. It's just how do we transition this into a new topic, and that would be complex numbers, because complex numbers can come up in a lot of places in different fields, and so polar form can get helpfful with that as well. So here's one more for you. If you want to try it on your own, you can. I've got, you can hit pause. Otherwise, I'm just going to kind of mosey through this. So I got, this as quadrant 3. Okay. And let's do r equals the square root of -5 squared root of 3, and then -5. What's 25 times 3? 75? I think so. I think so. And then that's 25. Oh, look how beautiful that is. So that's 100. Square root of 100. And so the radius is 10. All right. And then we need the angle. So tangent of theta equals -5 over -5 rad 3, which tangent of theta is rad 3 over 3 then. So like I said, I'm not going to do the inverse because I know I need the angle to be in quadrant 3. So I'm just going to pick an angle that makes that true, like an equation. So I'm going to go with theta equals 7 pi over 6. Then like I said, you just got to write it now, right? So I need these two things. I'm going to write it. So I'm going to say z equals 10, and then cosine of 7 pi over 6 plus I sine of 7 pi over 6. And that's it. Remember, don't multiply it out. So there you have it. I got these two, which are pretty nice because they don't really require a ton of work. So if I were to ask you where is this on the complex plane, you would just go 1, 2, 3, 4, and you would put a point here on the y-axis because there's no x part, real part moving you left and right. So what angle is this, right? Hopefully you can see that this would be this angle right there. So 3 pi over 2. So theta is 3 pi over 2. And the radius, since you're moving straight down, you can just count it, 4. So then you can say z equals, right, 4 cosine of 3 pi over 2 and plus I sine of 3 pi over 2. Okay. And you don't have to use like the tangents and the Pythagorean theorem just because it can all count. And the same thing can be said for this guy, right? Like if you draw a picture, here's -7 over here. And then, so that's pi. And then the radius is 7. And you could just write the number. Okay. So that's how you put a number, a complex number, into polar form. And then tomorrow we'll talk about, or Monday or Tuesday, we'll talk about how do you mess with these a little bit more. And then that'll be it. Okay. All right. So thanks. And I hope you guys have a wonderful day and be well. See ya.